Hello everyone. I don't see anyone has joined, so let's wait. I see Rohi is joining in now. Hi Rohi.
Hello.
Maybe let's give it a start. I'm sure others are going to pour in. So let me share my screen. Give me 1 minute. In the meanwhile, Rohi, did you had a chance to look into uh, the notes that I have already uploaded? Fine.
No, I did not get a chance to look at the yesterday's notes
Okay, no
on tech.
problem. Because anyways, we'll do a quick uh, revision of what we have done yesterday, and then we'll start from there. So let me just save the file. I did not save the file properly, so that's why it's not coming up. I think it will come up now. I hope you can see my screen.
Yes.
Yes? Okay. Okay. So let's quickly recap what we did yesterday because we did touch a lot of things with respect to this example, and we are going to take more examples. And as we discussed, we are going to look at how to calculate p-value. We are also going to look at a very, very bad table today, but the table is going to come very handy if we are going to do any manual calculations. Unless and until we use or we want to use Python or Excel or any other statistical tool, then we don't need the table because we have functions. Couple of functions we have already seen in Excel. If you remember earlier, we have seen the norm dot s.dist, norm.dist, and then a couple of functions which we are going to introduce today as well. So basis that and basis the z value, we can calculate the p-value and so on. So uh, these are the things that we are going to cover. But let's try to uh, cover a few points first. Firstly, I did not tell anyone until the last class about a certain type of tests that we are trying to do over here. So this testing that we are doing over here is basis the Z score. Right? So we are taking the Z value and then we are doing the test. So because we are taking the Z value and we are doing the test, this test is otherwise known as a Z test. Okay, so anywhere the rule of thumb is if we are taking any specific statistic or any specific measure by means of which we are going to do the hypothesis testing or any other exercise that's applicable in that area, then we are going to call the test by the name of the variable that we have taken. So because in this case we have taken z, right, we calculated zc. So that's why this test is going to be called a z test. Also, these kind of tests fall into a category. Uh, since we have used z value, we call that specific test as a z test, right? If we had used p value, we would call it a p test. If we would use t value, we are going to call it a t test and so on, right? So basis the variable that we are going to choose, we are going to name the test. Then the other thing that I should mention here, just for information, doesn't really matter whether what you're trying to call it, because ultimately they are all the same. What we are trying to do over here is we have some sampling distribution in place, and we are focused on certain parts of that distribution. Yes, we are looking into area under the curve, and we are looking into one side or the other side. Sometime after maybe basis the examples we are going to take, we may look into both sides, right? We may not even look into any side at all. That's also going to be one of the areas, or one of the examples that we can take. Now, depending on whatever we are doing, as you can see, we are trying to find out a value of z or x bar. So these are like points which are there on the graph that we are trying to be more interested towards or more focused towards. So that's why, since we are using specific points or values during the statistical testing, these so-called techniques are also called point-based estimation. Okay, so basically we are trying to do some form of estimation, although we are not really doing that. We are doing a kind of an inference, but then it is known as point-based estimation because we are taking some points. We are doing this inference or estimation basis some points, some values. So that's why it is point-based estimation. Right now, keeping this in mind, let's quickly go through what we have done yesterday. Right. So during hypothesis testing, point number one, we firstly formulate the null and the alternate hypothesis. Okay. Please do remember, if you get a problem well stated, this problem half solved. Right. So if we put the problem in the right way, we put the null hypothesis and the alternate hypothesis in the right way, I'm sure most of the problems will be resolved. Let's just try to put one liner over here. I'll say continued on 17th June. Let me see. I think someone tried to join. No, it's fine. Fine. So during hypothesis testing, we firstly formulate the null and the alternate hypothesis. I just want to mention, how do we formulate the null hypothesis and how do we want to formulate the alternate hypothesis? Okay. We start at the bottom up approach. We first do the alternate hypothesis and then we do the opposite with the null hypothesis. So these are like the paradoxes to each other, right? But alternate hypothesis is what I would like to prove statistically, irrespective of how much data or how good data, how bad data I have. Right? So let's say if I'm a floor manager working in DMart, and over my experience while doing rounds on the floor, I see that on average in the billing counter, a customer is waiting at least for 10 minutes. Then my claim, my comment here is that it's on an average taking 10 minutes for any customer to do a checkout. Now that's not the null hypothesis. The null hypothesis is the status quo. Status quo will always be, this is the status quo, which will always be against of what I think. Okay. So that's exactly what we did over here as well. You see, if I have taken a null hypothesis mu less than 29,000, this is not what my product manager handed me with. She is quite confident that where average monthly income is greater than 29,000 in the state of West Bengal, we must launch. So this is what she is expecting to do. This is what she is asking me to do. Right. So this becomes my alternate hypothesis, and the null hypothesis is exactly just the opposite of that. So that is how you define the question. So the moment you define the question, if it is properly defined with all the numbers and kind of things, or at least the context, then half of the problem is solved, because now you know on which side of the graph the thing is going to fall, whether it's going to be a one tail test or a two tail test and so on, and then you can solve it. Then we have defined alpha and beta. Alpha is going to be the type 1 error, and beta is going to be the type 2 error. All right, I'm going to introduce a few terminologies over here, which is point number 3, point number 4. Alpha is also called the level of significance. This is something we have looked into yesterday, right? The level of significance helps me determine how significant my hypothesis test was. It does not help me determine how good or how bad the hypothesis was formulated in the first place. Okay, so formulation of the problem is entirely up to you. If there is no test, there is no way you can validate, you can verify, there is no way, right? You have no tests to verify whether I have correctly formulated the null and the alternate hypothesis or not, even if they are represented in a mathematical way. I might be talking about it in English, but then if we look at it here, these are only numbers, these are actually equations, but there can't be any function. As of date, there are no functions actually which can help you determine the validity of the hypothesis itself, but you can determine how significant the test of that hypothesis was using the value of alpha, right? In the same way, beta, being the type 2 error, when subtracted from 1, gives the power of my hypothesis test. So if I'm able to calculate beta, which is just going to be a percentage, or which is just going to be a fraction because it is just a ratio of the numbers, right? So type 2 error is where I'm simply getting a ratio of the number. Same is the case with the type 1 error. So ratio is always going to be a kind of fraction value. If I minus that from 1, it gives me the power of my hypothesis test, right? So my target will be to maximize beta, right? Basis 0.3 and zero point 0.4, what do I see? I need to maximize alpha and beta only to a certain extent, or otherwise the number of errors are going to increase, right? So I need to control or maximize the values of alpha and beta, only to a certain extent, right? Because if I do beyond that, maybe I'll not be able to be 100% confident on the results, because these are actually the errors. These are something which shouldn't have happened but has happened. Next, one tail test is what the above example is for. Why? Since on the sampling distribution, we are looking at only one direction to test for the alternate hypothesis. So we are looking at only one direction of the graph. If had it been the case, we are looking for both, it would have been a two-tail test. There are tests where there are no tails, right? We are going to see those examples as well, at least one of them. Then the next point is, for any statistical test, a confidence interval of 95% is chosen. Right? Why is this chosen? Is because 95% of the data in any normal distribution is within mean plus minus 2 standard deviation. Confidence interval is where null hypothesis lives. We cannot reject it in there. For confidence interval 95% to 0.95, alpha becomes 1 minus confidence interval. So the formula of alpha is 1 minus confidence interval, which is otherwise represented as 1 minus, in this case it will be 0.95. So 1 minus 0.95, alpha becomes 0.05. So for any normally distributed data, any standard normal distribution is where I'm obviously going to say my alpha is going to be 0.05, because statistically my confidence interval will always be 95%. Now, what is the essence of this confidence interval? The essence of this confidence interval is something like this. I'll write this as essence. The essence of the confidence interval is, it gives the percentage surety of how much I am confident about my results. Now, this is contradictory to this line. If confidence interval is where a null hypothesis lives, then how can that percentage be a surety of how much I'm confident, right? This is kind of an opposite thing, I understand. But this point number A, or sorry, point number B is going to be applicable when we are doing that visual calculation. Ideally, if I get, or if I'm going to do a test with confidence interval 95%, I'm essentially meaning that I've done a test, and let's say the results, as we saw yesterday, that I think my results were what, greater than equal to 29,000, right? So we accepted the alternate hypothesis, if I'm not wrong. So because we accepted the alternate hypothesis, I'll say this statement to my client, or I'll say this statement to my company. We should launch where my alternate hypothesis is proved, or the average income per household is going to be greater than 29,000, which is the case in this state, and that's why I'm going to launch. So I'm accepting my alternate hypothesis, but by what level? So if you ask somebody a question, they'll say I'm 100% confident if there is a match between India and Pakistan, India is going to win. So that's the confidence that that person has, although there is nothing called 100% kind of a confidence. You can't be 100% kind of a confidence. There will always be that alpha level of error. The alpha value is going to be very critical when you define the error. So because you need to minus that from 100, that is the reason why this thing, this formula has come into picture, right? Because confidence interval is nothing but 1 minus r, right? And similarly, alpha is actually 1 minus confidence interval. So that's why in this case, I can only say I have proven the alternate hypothesis, all good, but I'm only 95% confident. So that is the essence of the confidence interval. It gives me the percentage surety of how much confident I am about my results. Now, let's get into the practicality. So the first way to test the hypothesis, we saw this. We are going to calculate ZC, or the critical value of Z. The formula to do ZC is what? X bar minus mu divided by sigma divided by square root of n, where X bar is the random variable. In this case, it was what? X bar is going to be, in my example, it will be 30,000 because that's what I have sampled into West Bengal. Mu is the mean of the population or the existing data. So mu in my case is what? 29,000, because I only have operations into Maharashtra. And I have already taken the data of the Maharashtra candidates or the customers I have in this state. And the mean comes to be 29,000. So that becomes my mu. Sigma is the standard deviation of the population or the existing data. Why I am repeating this statement is because you may not already have the entire Indian population in this context or in this example as your customers. It may well not be the case that you are going to consider the population of India as always the population word over here. So population is going to be whatever is there with you, right? Whatever is the totality right now. So it can also be called the existing data or the existing reach which you have. So maybe rather than data, I am going to call it reach, existing reach, right? Then n is the number of samples. In our case, it was 400. That's what my product manager did, right? She went into West Bengal, she took 400 samples. Now, once we have calculated ZC, we clearly saw, and this is where I would like to correct something which I shown you yesterday. It was just for the visualization or to the understanding purpose that I have done it in that way. Mathematically, that is not the right way. So I would like to correct that. So once we have calculated ZC, we check whether it falls in the critical region or not. So what did we do? We simply took a graph, and then we saw this is a one tail test, right? This is a one tail test because I have mu over here, right? I have a value which is somewhere here, or maybe I'm going to call this the alpha. So let's say this is my alpha, because until this point it is my 95% of the confidence interval. Then this becomes 0.05, right? If this is 0.95, until this point this is 0.95, this becomes 0.05, right? Now what I formulated is that this value is equal to 2.5. Now the ZC that I got, the critical value which I got during the test is what? Z of C is equal to 2.5, right? The calculation which I did yesterday, if you remember, the calculation which I did yesterday resulted into the Z value being equal to 2.5. So I said that because this is 95%, 5% is on this side, 5% is on this side. Now, this is basis the visualization factor. So if I take mu plus minus standard deviation, then 95% is here. So 5% is left out. That's why 2.5 is here, 2.5 is here, right? But calculation wise, that is not the case because this is a one tail test. So everything is like this. So 95% is here. From the edge of the tail until this point in time, this is the area where the null hypothesis lives. And this is my critical area. This is what I want to prove. So that's why mathematically this part becomes 5 or 5% area. And I have a value which is 2.5, which is less than 5, and hence it falls into this area. That is why I have accepted the null hypothesis. You can take it in either ways. Representation wise, this first way of doing things is correct, and mathematics wise, the second way of doing things is correct. Now, this is the only point, or one of the reasons why calculating a Z score has always been a problem, because you either need to visualize this or you need to draw a diagram like this. You need to get all the statistics in place and so on. So rather than using Z value or Z critical value as the determining factor, which comes out to be 2.5 over here, and then we calculate the fact that whether 2.5 is less than my alpha percentage value or not, and hence we reject the null hypothesis, which is all good. We will try to use some other better way, and the better way that we are going to look today is going to be the p-value. So if I take the p-value, that p-value is calculated out of ZC. And I've already told you I'm going to show you how we are going to calculate that, because there is a formulation. Right, we are going to have to do some kind of a normalization or a normal standard distribution kind of a function. I hope you are able to recall the function already. It is there in Excel, norm.s.dist. Right, if I use norm.s.dist, I will be able to convert a z value into a p value. Right, we have done this earlier when we have calculated in our examples, when we looked into z for the first time and we defined the formula. We went into Excel, we put the value of z and we put a value of true. Right, we put a value of true because this is a cumulative distribution that I am looking for. So the moment I put the value of z and true, if you remember, there was an example of breakfast cereals that we have taken. So we got the probability value. That's exactly the p-value. Right, that is exactly the p-value. And because we are going to play with this point estimation and that point in time, which in this case is the p-value, that's why this test is going to be called a p-test. Right, because we are using the p-value to do the testing. So rather than using z, we are going to use the p-value. Why is my p-value going to be good? This value is represented as a fraction, and it falls in the range of 0 to 1. It is clear that this is actually a probability because I'm 95% confident. So, and that's from where alpha has actually come, right? So alpha has come from the confidence interval. The confidence interval is where I said that it gives me a percentage, right? It gives me a percentage of how confident I am. So how much confident I am about my results. This is like the probability. I'm 95% sure that I need to launch the apparel into West Bengal. Right? So if this is the opposite, or it is just 1 minus that confidence interval, then this is also a probability value, and its range is always going to be 0 to 1. And this is always going to be a constant of 0.05 only, right? Because we already know that my confidence interval will be constant. Now, if I calculate a value which is a p-value, and this p-value also comes out to be a decimal, let's say 0.0062. If it comes to be 0.0062 or something else, which is less than 0.05, now this calculation, this comparison becomes easy. I can simply look at these two numbers and I can say, very good, my p-value is less than alpha. I'm simply going to reject the null hypothesis. And that's exactly what we are going to do when we look at the p-testing. Right, so that's exactly what we have written over here, especially with two-tailed tests. The use of ZC and then the visualization becomes very, very difficult. So let's make our life simple. We will continue with alpha, and then we are going to convert this ZC value into a p-value. Right, so p-value is nothing but the probability or the strength of occurrence of our null hypothesis. Clearly, lesser the p-value, higher is the chance of rejecting the null hypothesis. That's the ideology. Right, p-value is basically what is the probability of null hypothesis being true. That's all. The p-value is going to be the probability of how much the status quo is correct, which means how much I am wrong, how much my intuition is wrong. My intuition is what? The alternate hypothesis, what I would like to prove. Right, it means how much this is wrong. Right, so the opposite, the ulta, is the null hypothesis, how much null hypothesis is correct. So my idea is what? Clearly, I have to minimize the p-value. The less the p-value, the better. The more closer it is to 0, I will be very happy, because then I can safely reject the null hypothesis. Right, now once I calculate the p-value, as I have just shown you in the diagram, I simply calculate the p-value, compare it with alpha. If it is less than alpha, we reject. If not, then we cannot reject. So we don't say we accept the null hypothesis. We said that we did not find any good data that we can be 95% confident that we can reject the null hypothesis. Right. So let's look at a quick example into Excel. Then we will go back again with some more examples. Right. So let me just share my screen. So let me share Excel. Right. So you can ignore this field now. So that's why I'm going to hide this. Expected z-score is something I have not explained yet. We can't really ignore the z value entirely, although we are really infatuated right now with the p value, but we can't get rid of z because z has a very, very interesting thing which we are going to look at. It's called the z table. And that z table already gives you all the range of p values. And that's why it can't be simply ignored out of our lives. But what we can do is that, let's say in this example that we have already looked into yesterday, my z value came out to be something like 2.5. Right, I calculated that z value which came out to be 2.5. Let me just format this part so that it looks nice. Okay, so my z value came out to be 2.5 in the last exercise that I have done. Is which I would like to know what is the p value. So I already know what is the formula for this, norm.s.dist. Okay, norm.s.dist. Why? Because it is a standard normal distribution. Why it is a standard normal distribution? Because central limit theorem is applicable on it. Why is central limit theorem applicable? Is basis my sample size. My sample size is more than or equal to 30. In this case, it is 400. It is even more than 10 times of the expected value. I should have had 30 samples. I not only have 300, I actually have 100 more than that. So it's like 100 more than 10 times of the expected value is what I have in the sampling size. Hence, I can be sure that central limit theorem fits over here, empirical rule fits over here. If central limit theorem fits, it is a standard normal distribution. Hence, I'm going to simply put the value of z. Now, in Excel, how do you put the value here? It is cell number A2, right? This is cell which contains the z value. So I'll simply say A2, and then I'm going to say 2, right? It gives me a p value, right? If it gives me a p value, this is where I'm going to come to a conclusion now. Okay, let me just see if I have done this calculation properly. Let me give me 1 minute. Let me just see. Where is my, just a moment, huh? Open. Oh, yes, yes, of course, of course, of course, yes, of course, yes, of course. Now, there is one thing that I have actually forgotten to do. This is something we did when we did the Z calculation. So it is my mistake here. It should not be a norm.s.dist. It should be 1 minus. Why? Because we did this when we calculated the Z score earlier. I accidentally forgot that. Let me just correct myself. I'll again draw this. My Z C is somewhere here, and this is the direction in which I'm increasing. So if anything is on this point, then clearly it is going to be a negative or 1 minus, because this is on the progression side, right? This is what we have seen already. So that's why it should be 1 minus. If it is 1 minus and the value is so small, and my alpha is what? Let me just write it over here. Alpha. Sorry, alpha. Right? Alpha value is 0.05. Right? If this is less than this, then we accept the alternative hypothesis. That's my intention here. So 0.0062 is really, really less than 0.05. And hence, I can clearly say I can reject the null hypothesis. Right? This is one way of doing. The other way of doing is using an expected z-score kind of a thing. What is expected z-score? Expected z-score is something like this. I will use a formula first, and then I'm going to explain why I did that. I'm going to take a formula which is this. I will return the inverse of the standard normal cumulative distribution, which has a mean of 0 and a standard deviation of 1. So I'm simply trying to do the opposite. Okay, I'm simply trying to do the opposite of p-value. So if I do this and I take the probability, which is 0.05, right? I put the probability of the alpha value. So I get a value which is minus 1.648, right? If using this value, what I can do, I believe this should be minus actually over here because I'm on the other side. No, sorry, this will not be. No. So using this expected Z score, I can also try to figure out what is the correlation between the Z value and the expected Z score, and then I'll try to accept or I will try to reject the null hypothesis. Right now, this is also going to be a difficult thing to do. Why? Because I don't know how these two are going to relate. Right, and hence what I'm going to do, I'm going to open something which is known as the Z table. And this is where, as I said, the usage of Z value to do a direct calculation without looking at P value. Here I'm not really looking at the P value. I've simply inputted 0.05, which is my alpha, right? Because my confidence interval is 95%. So I'm trying to make my life complicated by doing what? I'm taking again that Z value, and then using that Z value, I'm trying to calculate something. And that something is the is the critical Z score, and it is quite complicated already. And to solve that, because Z has no scale, I will need to use a Z table. I don't know whether you have already seen anywhere this table, so let me share this. So this is what a Z table looks like, right? If you look at this is what the Z table is going to look like. Now, how do I read this is a very, very difficult task to do. I'll go back to my Excel sheet once, although you won't be able to see it now. It gives me a critical score of uh, minus 1.644. So minus 1.64. So minus 1.6 is this line. And then 0.04 is going to be what? To this line. 0.0, 0.1, 0.2, 0.3, 0.4. Right? So this is a way in which using the Z table, you see minus 1.64 is actually 0.5. So 0.05 was my alpha value. This is how you convert a probability value into Z value or a Z value into probability value. So if I have a probability value which is minus 2.5, in this case it will be minus 2.5 only, right? Because I am looking into the right tail. So that's why I did a 1 minus thing. So minus 2.5 is going to be 0.0062. And that's exactly what we found out in our Excel sheet as well. If you remember the value which we found out in our Excel sheet, let me just go back to the Excel sheet once. In the Excel sheet, we found out the value which is 0.0062. So this is one way to convert any Z score on any expected Z score into this value. The expected Z score came from where? This alpha value. And this Z value came from where? This value. It can be the opposite as well. In this calculation, what I've done, I've simply used this function and I have calculated the P value out of the Z value. Had it been the case, you have the P value, you can also calculate the Z value. You saw it here, right? You have the P value. This is nothing but the probability value, which is represented as alpha. You have converted it into a Z score. So as you can clearly see, usage of column A or column C, these values are going to be very complicated. Or you always need to visualize it. And then there will be corner cases or the situations where you will have two-tailed tests and so on. You will get simply confused. Hence, I would strongly recommend what we preferably used in the industry, although there are few statisticians who are actually challenging this way of doing. They're saying there are other best or other better ways to do let's say hypothesis test. We are going to always look into them as well. They do not completely agree with the essence of the p-value. There are some reasons which are quite valid from their experience, from their perspective as well. But at least with comparison to the Z value and kind of the confusion it has created, I think looking at a p-value is much easier, right? Looking at a p-value is really much easier. I have the formula, I know in which direction it is. Basis the direction, I either take the formula or I do a 1 minus, and then I simply compare. Is this less than alpha? If yes, then I accept, uh, and I can accept the alternate hypothesis. Hence, I can say I have rejected the null hypothesis as part of the hypothesis test. Right. So, continuing with the p-value, let me take some more examples. Okay. But first, let's try to do some kind of notes. Let me go back to my notepad. And as I said, one very important, okay, we have only uh, approximately 7 minutes left, which is fine. Let's see how much we can do. So we saw in the first point only, during hypothesis testing, we firstly formulate the null and the alternate hypothesis. So let's take some examples of these, and then we'll take a few more examples of hypothesis testing itself. Right? If you have any doubts, please do let me know. It's fine if you have doubts. So now let's take some examples, and maybe you can unmute yourself as well, Rohi. So I'll just post the questions here. I'll just create some questions randomly, and you can try to answer them maybe by speaking, or maybe you can post it into the chat window. All right. So let's take a few questions. I have gone to a supermarket. Again, I'm going to go back to that same example that I am actually, this time, let's say I'm not the floor manager. I am actually a customer in a supermarket. Being a customer in a supermarket, I am worried, let's say, if the waiting time in billing queue is more than 15 minutes, right? So being a customer, I'm actually worried whether my waiting time is going to be more than 15 minutes or not. But you can take this as a question: is my waiting time going to be more than 15 minutes as a customer? Is my waiting time in the billing queue going to be more than 15 minutes? Now, in this case, right, I would like to ask you, if you were doing the hypothesis testing, how are you going to formulate the null and the alternate hypothesis? Go ahead. If you would like to give it a try.
Yeah, null hypothesis will be that time will be less than 15 minutes.
Okay. And the alternate is going to be greater than,
Yeah,
right? So because this
greater than
should be,
equal.
yeah, so it should be either this or it should be this, right? So any one of them is going to work. So you are right. Either it will be equal to here or equal to here, right? Let's take the second one. The second question is, I went to Chennai and I have a question on people who are still using, let's say, color TVs, because they have already moved into digital TVs and smart TVs and so on. But I could see a few friends of mine who are using, let's say, color TVs. So my question is the proportion of uh, Chennaites using color TV more than 0.4, or maybe even better, I would like to be a bit optimistic, less than 0.4, because we are using the digital TVs, right? So it should ideally be, my intuition should be that they should already have moved to the digital versions. So it should be less than 0.4. It means less than 40% of people are using the color TVs. So in this case, how are you going to define uh, the problem?
Mu less than 0.4. It's not.
Okay. Okay. So mu less than 0.4 is going to be my the alternate one, right? Or the null one.
I think it should be null.
Okay. Okay.
Mu less than 0.4.
Then the other side should be something like this. So in this case, what I am trying to prove, right, is going to be my alternate hypothesis. So mu less than 0.4 is going to be my alternate hypothesis. Why? Because that is what I'm interested to prove. Right? The opposite of alternate is going to be the null hypothesis. Right? So simply put, you take the question and you see what you're trying to prove, it becomes the alternate, and the opposite is going to become the null. Maybe we won't have time for the point number 3 and 4, but let's quickly try to understand this part, because this terminology is now going to change a little bit for this kind of a question, because there is a proportion thing, or otherwise your attempt was right, but this will not be the null hypothesis in this case. It should unfortunately be the opposite side. So mu less than 0.4 is what I'm expecting. Is the proportion of Chen nights using color TV less than 0.4? Because I've already given you a context, right? The context is, I know that people are moving on to digital as soon as they can. If they can afford, they are already into the LED TV or a smart TV kind of a generation. So this is what I'm expecting out of the data. I don't know whether I'm going to prove it right or not. Right? So that's why this becomes the alternate hypothesis and the opposite becomes the null hypothesis. Right? Now, this mu will not be applicable. We just have only 1 minute left. So let me just quickly tell you. In this case, mu will not be applicable. There is a deliberate reason why I use this example with the proportion, is because whenever you have a proportion, right, you don't explain it by mu, because mean is not applicable on a proportion data. In this case, you represent a proportion in phi. So phi is just another mathematical notation. I don't know whether you have seen this earlier. It looks like this. Right? So any proportion is going to be defined by phi, and any mean is going to be defined by mu. So in the upper case, a mean was really required because this is just the average time, my average waiting time in the billing queue. But in this case, this is the proportion of the people in Chennai who are going to use the color TV is less than 40%. Right? So that's why in this kind of a case, you just have to remember that rather than mu, we are going to take phi. Right? I
Okay.
think we will need to close here because we don't have time left. So maybe if you have any questions, please do let me know. Yeah, and let's continue tomorrow.
Okay. Okay. Thanks.
Thank
Thanks,
you.
Mohammed.
Thank you.